Welcome back, Algebra Express. We are in the new textbook this time. We are in Rockswold 1.4. We are doing types of functions and rates of change. Okay, so in this one, we are continuing our lesson on linear functions. So we're going to talk more about linear functions. We're going to talk about a specific type of linear function called the constant function. We've already talked about this thing already. So let's start with the example that they give us. So if we're looking at this thing, they give us an example of two cell phone plans. So this might seem pretty steep, but not that long ago when I was in high school, these are probably about what you'd pay for a cell phone plan. Yeah. They would charge you per minute usually. The unlimited plans are something that came along like after the charging them per minute sort of thing. And so they started off a bit higher than the charge per minute plan. And so you used to have to kind of compare between, do I want to pay for per minute or do I want the unlimited plan? And so what it looks like here, they give us this thing. And if we're looking at the unlimited, it makes sense with its name. We're only going to pay $1.99. If we try to figure out slope, so my x-axis is going up by 100. By 0. So if I try to figure out slope, I can try to do my change in my y over my change in my x. So each time I'm going to get 0 over 100. So this is giving me a slope of 0. And so the first question they ask is something like, find and interpret the rate of change for both plans. And so we're finding the rate of change, aka the slope on this thing. And so for this thing, my slope is 0. So what does that mean? If I want to 99. That might also give you some indication about what this thing sort of means. And so what this means is that we're going to pay a flat rate of $1.99. So this is never going up or coming down. It's going to stay at $1.99. And so it's going to stay at this constant rate of $1.99. So this is what is known as a constant function. It is a specific type of linear function where the slope is 0. That's all that means. And we'll see on the graph another reason why they probably call it constant. So we're looking at this thing. They want us to interpret. The plan does not charge per minute, I guess is one way to say it. So the unlimited plan does not charge a per minute rate. Or you could say they charge $0 per minute. That's also another way of saying does not charge. Both of those would be acceptable. And so we have the unlimited plan. So maybe I should say this is unlimited. The next thing is the pay per minute plan. And so I did a little prep over it for you. When you get your class, you can say yes. Comments, you can say I cut an entire strip of paper. So much labor intensive. Okay, so now we're looking at these two things. Ignore the middle thing and ignore the horrible joke. Now we're looking over here. We're still going up 100 each time. Now we're going up 20. And so if I want the slope of this thing, over 100. The change in my y over my change in my x. Okay. It's in my head. And I said, okay, it's probably best if we're talking about word problem and we're talking about money to go ahead and put it in decimal format. And if I do this, this is my pay by minute plan. So I'm probably cramming a lot of words in a lot of space. But this is a pay by minute plan that I'm doing here. And so what does this mean? How do I interpret this? So what does this mean about what this thing charges? So the plan's going to charge you how much? It's going to charge you 20 cents per minute. Oh, man. And if you didn't have a phone bill for $200, I don't think you grew up in the early 2000s. Like, that was something that I think almost like every kid probably went through at some point and probably got yelled at about. You don't really realize how many text messages you send when you're just being a 17-year-old goober. The plan changes. Okay, so if we do a little more figuring, I think we're going up $20 each time. So if we want to figure out this one, I believe it should be what, $19 is its fee. So there is a flat rate of $19, and then we're charging $20 per minute. Oh, dang it. And so they map this sort of thing out, and you can see right here is what else. And so they're just plotting these points onto a number line, drawing the line through them. And so this is the unlimited, this is the constant function I was talking about. It does not change the value of 199 that they're charging you. It is a flat, zero slope line. It doesn't change, and that's why it is a constant function. So a constant function is really just a specific type of linear function where our slope is zero. So if our slope is zero, and you fill in the zero slope to your linear function, to your slope intercept form, this thing is 0 times x. We're not going to see this. We're just going to see that b there. And so the constant function, like I said, it is really just a specific form of linear function when your slope is 0. It is that flat horizontal line is what they're talking about. And so now we get to play everybody's favorite game. Is it constant, linear, or non-linear? All right, so where am I? Maybe it's sort of like a Venn diagram might help. Maybe if you're picturing these things. So I'm seeing like and so I'm thinking about sets and subsets maybe. This is a sort of picture that maybe goes on in my brain, right? I have a big sort of set of functions. Within that, I have linear functions. Within that, I have constant functions. Okay. And so I want to think about, is it linear? Is it constant? or is it more specifically constant, or is it nonlinear? And sort of going back to linear, remember that all linear functions have a slope which is constant, right? Linear functions have a constant rate of change. These will each give me equivalent fractions, which will give me equivalent slopes, right? I might have to reduce the fraction a little bit, but it will be the same fraction. This is the same rate of change. So if I don't draw something curvy, if I do the same thing with something here, I take 2 points. You might notice if I draw that triangle versus if I take another 2 points out, try to draw my triangle. They are going to be different steepnesses. These triangles are obviously different. They're not going to be similar triangles like we get with a straight line, right? So if we have something that curves, that is nonlinear. We're not going to be able to do our slopes. And so we say that linear functions have a constant rate of change or a slope, right? So it is implied when we say slope that slope is a constant rate of change. So with nonlinear things, and we can do other things with this, right? If we want to find the slope between 2 points, we can take these 2 points and we can absolutely plug in our slope formula. And we can figure out, well, if they were a straight line, what would that look like, right? These are called secant lines, and you might notice like this is a secant line and this is a secant line. This one is more steep than this one, right? We're looking at our lines. This is zero slope. We're increasing our slope, positive slope, until we get to like our undefined, right? And then we start off with like what, negative slopes and go the other way. Ooh, move my hand a little bit. So we go negative slopes, go the other way until we go to larger negative slope and larger negative slope till we hit the undefined line, right? Okay. So we can look at maybe like 2 consecutive points and look at the slope in between those, but they're not going to be the same if this is not linear, right? So these things have a constant rate of change, which is known as the slope. So let's look at these things. So we have talked a little bit briefly about what these look like. So this is a absolute value function. So we know they look sort of like this. They look like a mean. That was one of the graphs on the previous Marcheck 3.6, I believe, at the end there. It was one of the graphs that they had that you should have studied. So it looks like this. It has some shifts, and we haven't talked about what these shifts do. But this is a left and right shift, so it's just not going to be on the y-axis. I believe it's shifting at left 3. Or like that. So if you wanted to, you could probably graph it with the t-chart. The more important thing to ask yourself, I think, is it constant? This is not a horizontal line, so definitely not a constant function. Is it linear? So this one might be a little bit harder to ask. Is it linear? And so the previous thing I said about linear functions was that linear functions have a constant rate of change or they have a slope. And so we try to do that. A negative slope. If we take 2 points here, we're going to get a positive slope. And so that in itself is telling us the sign of the slope isn't even the same. So this is definitely not linear. And so there's only one other thing I can check off here. So this one has to be nonlinear. So it's either constant, linear, or nonlinear. It would have to be nonlinear. Okay. So going back through them. Now we're looking at x squared minus 5. Is it constant? Is it linear? Is it nonlinear? So a square function, talk about, this looks like a parabola. If we're just moving it down 5 units is one way that you can think about it. But we haven't gotten there yet. The more important thing is to know that this makes a parabola. And so if you know this makes a parabola, right away you can tell me it's not flat, it's not constant. It does not have the same rate of change. Right? Just sort of like that previous function, there. This one is going to be a taller triangle. It is a higher rate of change. And so it is not linear. It is a square function. It's nonlinear. And I don't know if I said it explicitly, but another way to look at whether it is linear or not, if we look at all our previous linear functions, they were all first degree. I misplaced my first page already. Another indicator is if we look at the power on our variable, we're all doing first degree. It's to the first power. There's nothing being raised to a higher power, right? Like a square or a cube. So that's also another really good indicator that this guy is not linear, right? And the thing that makes him not linear is a square. This guy, it looks like he might be linear, but the thing that makes him not linear is that absolute value thing happening. This thing, is it constant? Well, it doesn't look like y equals to some number. But linear. So how much time I want to spend on this? But this is linear. If I want to give me an do that. So I think that's probably a fair question to ask. So what is my slope? What is my y-intercept? If you tell me this thing is linear, it is easy to pick right off 2 and a minus 6. Okay. Second to last one. We have an absolute value. We have a minus 4. And so we've had one absolute value already. And so if we're looking at absolute values, this is another absolute value with a shift. We hadn't talked about the shifts, but it's shifting it down 4. It doesn't really matter how it shifts it. If it's an absolute value, it's an absolute value. It looks like a V. And if it looks like a V, that's definitely not constant. It's not linear. And so therefore, it's not. Last one. We have a function that looks like z of x equals pi. Okay, so graph this. This is like y equals, and pi, approximate it to like 3.14. So if I'm doing this, and I'm drawing a really horrible graph, work with it, and it'll work with you. So what does this graph look like? It looks like y equals, and I know it's pi, and it's a weird number, but pi is still just a number. It is an irrational number, but it is still just a number. So what we want to do is we want to put a line like that. And so y equals pi. Y pi. Okay, and so that's a lot of talking to say. This thing is a constant function. It does not go up and down. It is just y equals to that 3.14. Z of x equals pi. You might notice there is no x in this thing, even though we're trying to plug an x into our function. There's no x to plug in. It's just a number. Okay. And so we move on to page 3. Oh, this is a student activity. So hopefully you're pausing and doing this all on your own before I even talk about it. But this first one should be fairly simple. So what kind of equation can be graphed using a slope and y-intercept? We can graph a slope and y-intercept. We know linear things have a slope. We know that linear things have a y-intercept. And if we know those two things, we can graph that entire line knowing those two facts. We have done it before. We're probably about to do it again in a couple minutes. And the next thing we need to ask ourselves, what about nonlinear? If we have a y-intercept, I can put my point on my y-intercept. I can do my slope to find all my line if I have a line. If it's not a line, and this goes back to this sort of thing, can I use slope to find my other points? No, I can't. I cannot. It does not work. It does not have a constant rate of change. I cannot do that sort of count up and over sort of thing that we do with the line. It doesn't work. So that's what they're trying to get at there. What does the graph of a constant function look like? I want to say like just the most kind of flat. I don't know. It looks flat. Probably the better mathematical term. A horizontal line, zero slope. These are all sort of descriptors that you could probably say. It looks constant. It doesn't change up and down. Describe a way of graphing equations that cannot be graphed using a slope and y-intercept. So, at this point, we really have like one sort of option to do it by hand, right? So if we're doing it by hand, what do they call them? T-charts? Whatever you want to call it, we got to make a T-chart. We got to graph them out. We got to plug numbers into our equation. We got to try to figure it out. And that's if we're doing it by hand. If we have technology, the technology can do some of that work for us. But, you know, don't want to be too over-reliant on technology to do things. It should help you with your understanding. It shouldn't prevent you from getting a deeper understanding, right? Okay. From the table on the previous page, choose one linear and one nonlinear equation and graph them. So I think we only had one linear equation on the previous page, and I think it looked like something like 2x minus 6. H of x. X minus 6. I guess technically the z of x equals pi is also a linear function. I don't know anything about that. But the z of x equals pi is up there too. I guess that's technically a linear function. It's a constant function. I'm going to graph this one, though. I've already graphed the pi. The y is pi, right? I've already graphed that. So let's do the linear, and for the nonlinear, what did I do? I think I chose that first one on there. Y equals x plus 3. Absolute value of x plus 3. And so if we want to graph the linear, this is what they're talking about. We know how to graph linear things. We go to our y-intercept. Trying to write out where to go. Is 2 or 2 over 1. I can go up 2 for every 2 over 1, up 2 over 1. Probably just enough to get my my x-intercept on there. I have my y-intercept already. Probably doing this on my other points too. Ta-da! It's not too bad, right? There's another point. There's another point. I'm starting to get off a little bit. Okay. Good enough. As long as you put a few points on there and I can see your points and I can see your points are matching the slope that you were talking about, I'm not going to be like that picky with all these other things, right? Draw it as good as possible. That's what I expect. Okay. That is 2x minus 6. Okay. So for the other thing, we want to plug in some points. For my x and y. If I plug in 0, I'm going to get the absolute value of 0 plus 3. And that is the absolute value of 3. So if I get something like 0, 3, I plugged in a few more points. I don't want to do this. We've done this a few times. So I'm going to skip and plug in a few points. I think I went to 3 and 5 in the negative direction. So I'm getting minus 5, 2. I'm getting minus 0. I'm getting 3, 6, and 5, 8. So if it's nonlinear, we don't really have a tried and true sort of way to graph these things yet. So we plug them into a t-chart and we start grabbing some points and trying to see what these points sort of look like. What sort of function are they looking like? And then the other thing is we do know the sort of like general shape of this thing should be a V. And we know that because of the previous lesson. So if we're looking at this thing, I'm doing minus 5, 2, 4, 5, 2. I'm doing minus 3, 0. I'm doing 0, 3. I'm doing 4, 5, 6, 6, and 5, 3, 4, 5, 6, 7, 8. Okay. So we know this thing looks like a V. It is going to hit and rebound, sort of like, I don't know, a full ball or ball. Highlight wobble. What is that? Squash. That's what it's called. I don't know. Something with the ball hitting the wall and bouncing back. Dynamic collision. Actually, I think it's a static one. I think it's static because it doesn't move. The wall don't move. I think dynamic is when both objects move, but I could be wrong. It's been a minute since I took physics, so don't quote me on that one. Okay. So this is my graph. This is a linear graph. We can do it with slope and intercept. And so hopefully this should be a little bit quicker than doing nonlinear. And the last page. So we're going to talk a little bit more about slope, and then we're going to talk about going in a little bit different direction for those last two, or I guess 4 problems. We're going to talk about intervals of increase and decrease. Okay. So if we're looking at this guy, we want to find slope on a table, we got to find our change in our x, and we got to find our change in our y. So our change in our x, I believe, is going up by 2 each time. It is by the same amount. If we're looking between, I believe First one goes down by 4, this one goes down by 3, this one goes down by 4, and this one goes down by 4. And so they say find the rates of change between adjacent points, determine whether the function is linear or nonlinear. So we're trying to see if this thing is linear or nonlinear. We have found the right numbers to find our slopes. Minus 4 over 2. Or minus 3 over 2 are the first two slopes. Same thing as a minus 2 over 1 or a minus 2 slope. This is like a minus 1.5, right? So those two are not the same numbers. And so if they're not the same numbers, this does not have a constant rate of change. This is not linear. So I know, I just thought about it. I don't want this to be like a point of confusion. I know I'm using M, but what I'm really doing is I'm doing that sort of, I'm looking in between each two sort of like adjacent points, and I'm looking at the slope between these two things. So I'm looking at this slope, and I'm looking at this slope. So I know maybe it seems like I'm being presumptuous by saying M, but I'm not actually assuming this thing is linear, right? I'm trying to see if it is linear. And it's not linear because these are not the same numbers. So if all these were the same numbers, we would say linear. Since this is different from this, well, even since this is different from this, since we're all going up by the same X amount, these are not linear, right? On the other hand, I've written stuff all over that. Grab another sheet of paper, right on top of there. We want to look at consecutive points here. Up 3, up 2, up 1, up 6, up 4, up 2, up 6. Now I'm looking at this. I want to do my change in my y over my change in my x. So I have basically 4 different slopes I can write out. Same as the previous one. Same approach. So I have either 6 over 3, I have 4 over 2, I have 2 over 1, or I have 6 over 3. So in this one, they're not giving us a constant x rate like they gave us in the previous one, right? That's not going up by the same amount. We're changing the amount that we are going up. And so we have different amounts. But if we're looking at each one of these, 6 over 3, 4 over 2, 2 over 1, simplify all of these, they're just the number 2, or 2 over 1 slope. 6 divided by 3 will give you 2, 4 divided by 2 will give you 2, and 2 over 1 will give you 2. And so since we're getting the same slope between each consecutive points, we can assume this thing overall is probably going to be linear as long as this pattern continues, right? Okay. And so I know I probably stopped at 2 slopes here. I could have wrote out minus 4 over 2 2 more times if I wanted to, right? I have it 2 more times. Okay, so maybe I was being a little bit lazy there. But as soon as I see one that doesn't match, it doesn't matter. It's already not linear, right? So for intervals of increase and decrease, We're talking about where the y quantity increases or decreases. So my word of advice to this is kind of like, we just want to talk about where it goes up or down, increase or decrease. So for the most part, we're not even going to look at the y-axis. We're going to look at where this thing goes up and down, and for where it goes up and down, you want to give me the domain of where this thing goes up and the domain of this thing where it goes down. And so this goes back to the domain and looking at intervals and picking out the domain, the numbers from your x-axis for your domain. So I want to talk about this thing. I want to look at this graph. We're reading it left to right. We're starting here at -2. This thing is going, hopefully you can see it, it is going up. It is going up until right here. And as soon as we get here, we start going, this is what we call down. This is going down. And as soon as we get here, it stops going down and it starts going up. So there are these points, these certain like turning points that are happening in here. And I believe they're happening like right there and right there. So if you want to mark off those points, if you want to do something like this is where we're dividing our interval, right? From where it goes up to where it goes down, those turning points. Now we want to talk about intervals of increase and intervals of decrease. So first thing is increase. Where does this thing go up? So this thing is going up. We're starting at -2. And it's going up until here, which is my quantity of 0 in there. That's my origin. So from -2 to 0, we are going up. Don't look at your y-axis. Ignore that thing. Ignore the numbers there. Don't cross your eyes and look at the numbers, right? We're only looking at our x-axis. And our x-axis says from -2 to the 0, it's going up. Here, it's not going up. This is all down, down, down. Here, we start going up again. So this is going from 5, and it's going up until 8. So from 5 to 8. And I want to talk about the interval from 5 to 8. And I want to talk about these things together. I have to put it in. I think sometimes the book might use, I think this is one of the intervals the book uses a comma on sometimes. So they might be using a comma instead of a union. Either way, it's good. You're talking about both of those sets. As long as you get both those intervals on there, that's what I really care about. Intervals of decrease. So we talked about where it was decreasing. It's decreasing from here to here. So this, again, ignore your y-axis. Don't pick numbers off of this. We're getting the y quantity going up and down, and that's all we care about. We don't even care about the numbers so much. So what is the x quantity where it starts going down? Way over here. The x quantity here is 0. It's going down until we hit the x quantity of 5. And I don't know if this helps or not, but our entire domain is going from like a -2 to an 8, right? And so we should be able to look at this thing and sort of like piece these things together. We got a -2 to 0. And then we pick up from our 0 to our 5, and then from our 5 to our 8, right? And so hopefully we talk about our whole domains more in there. And so sometimes that might help make sure you got all your pieces. Like these things sort of match up, right? A little bit. Okay. Similar sort of approach here, except now we got like an arrow jutting out way over here. Whatever could that thing mean? I don't know. Let's think about it. We're starting from the left. We're coming in. We're going right. And so we're going right on this thing. It's going from like minus infinity out here. And we're going to be going down all this way. Well, that was a long way to go down. I'm sorry. And we're going down until we hit this point. When we hit this point, we start heading back up again until we hit this point. We level out and we start going down again. And so, where did my red thing go? Right here. If we want to look at this, you want to draw your line. Enjoy your line. Find your domain. Where you go up and to where you go down. Put the paper on there so that students can see it. Okay. We want to do the intervals of increase. So where does this thing go up when we go left to right? Well, throughout here, it's going down, down, down. It starts going up here. So the x quantity is going up. Again, don't look here. Ignore these numbers. The x quantity is going up starts right here at a -2. It's going up throughout my pen, and it is going up until here at 2. So from -2 is where this thing is going up. I want to talk about the interval. And so I've kind of just thrown this on there, but I haven't done any hard brackets, if you notice that. So when I talk about the interval of increase, interval of decrease, and this might change what math professor you have and what book they're using and what they think about the endpoints. But I like to consider the endpoints separately, and there's good reasons for me doing that, and there's good reasons for why other mathematicians do that. And because we do have to make those considerations kind of separately when we start doing higher math. So just pointing this out, since we're here, I do not include my endpoints when I talk about my interval of increase and my interval of decrease. That might be different depending who you get. So the last thing, the interval of decrease. And so I kind of talked about this. This is the weird thing that they added to this one that the previous problem didn't have. We're coming out here from the negative side, way over there. It keeps going and going. So we think about that as negative infinity. And it is going down everywhere until we reach the -2. And if you put that, you will be about half correct on this thing. Because it goes down here, it's going up, and guess what? We have another little piece here we got to talk about. So it's going down from here to here. My x quantities is going from 2 to 4. And that's the last sort of problem on this thing. And so we talked about like sort of nonlinear functions and just like carrying a little bit further. Maybe something like that. Is we talked about this finding like slopes between consecutive points. So if I want to draw maybe the slope of that thing versus maybe like the slope of this thing, these 2 points, I can take these sort of slopes here, or it's also the slope of the secant line. They're one and the same thing. And we can talk about the rate of change between 2 points, right? We can talk about the slope between 2 points. And so with math, we like to do really weird things. And so what if I keep bringing this point in, is my next sort of question. What happens? What happens if I keep bringing this point in? What if I just talk about the rate of change happening at this one point? What if I make this gap between these 2 points approach 0? Is what they're essentially going to do. And if you can think about that, you've thought about calculus already. So that's what they do in calculus. That's called the derivative. It means like the instantaneous change that is happening at that single point. And so it's a weird sort of thing to think about. It's something that I know you probably just heard me say it, and you're probably like, I don't even know what that guy's saying. It's something that you're going to have to sleep on for a minute, probably. But if we want to talk about instantaneous change and what's happening at a point, and that's also like going back into why I don't include the endpoints on here, right? Is it going up or down at this point right here? Yeah, good luck answering that without some calculus, right? It's actually, if we take the tangent, it's going to be flat right there. And so it's arguably it's neither going up or down, and so I don't like to include it. And so that's why all my brackets here are going to be soft brackets when I talk about intervals of increase and decrease. And I hope to see you in class. That is all I got for you today. Take care, and I'll see you soon.